Question number 10. We want to determine whether this series converges or diverges. Sum of n from 2 to infinity, a sine of n minus 1 over n squared plus 5. So this is going to be a little bit of a tricky one. What we're going to end up doing, is that we're going to use the limit comparison test, not once, but twice. So I'm going to kind of sketch out all the details of the big picture, and then we're going to go back in and fill in all of the little nitty-gritty things. So the first thing to realize is that as n gets really, really big, n minus 1 over n squared plus 5, that's getting closer and closer to 0. The limit as n goes to infinity of n minus 1 over n squared plus 5, that's getting close to 0. And we also know the following fact, that sine x is approximately equal to x if x is close to 0. So what this is going to suggest that we do is, because n is getting big, the argument of the sine here is going to 0, we're going to end up comparing this series with the following series, the sum of n from 2 to infinity of n minus 1 over n squared plus 5. Now, I haven't yet done the formal work here to show that we're allowed to do this, but I will just say we're going to see in the long run these two series are going to have the same behavior by the limit comparison test. Also, okay, so we have this here. Well, that minus 1 is kind of a red herring. That plus 5 is kind of a red herring here. This series should have the same behavior as the sum of n over n squared, which is, cancel out the factor of n, 1 over n. This is the harmonic series. How many times have we seen this? This diverges. So what we're going to do right now to fill in all of the details is that we have to use the limit comparison test once to show that these two series have the same behavior, which is going to result in saying that this one diverges. And then we'll use the limit comparison test a second time to argue that these two series have the same behavior, which will show that this one diverges, and we will be done. Okay, so let's get to work. So for our first application of the limit comparison test, we will have this be a sub n, and this be b sub n. Doesn't matter which one we call a sub n and b sub n. But the limit as n goes to infinity, I should point out everything here, the hypotheses of the limit comparison test are satisfied. They're both positive sequences, for example. The limit is as n goes to infinity of a sub n is 1 over n divided by b sub n, n minus 1 over n squared plus 5. Limit as n goes to infinity of, flip that upstairs, n squared plus 5 divided by n times n minus 1, n squared minus n. And it's pretty easy to see that this limit here is equal to 1. You could use L'Hopital's rule. You could just look at the leading coefficient is 1 in both cases. They're both, the numerator and denominator are both polynomials of degree 2. So we are able to conclude here that this diverges by the limit comparison test using this series. So what meaning does this 1 have? Remember, the limit comparison test says that if you have, if the limit of the ratio of an and bn is anything that is strictly positive, not 0, and not infinity, 1 certainly satisfies that, these two series are going to have the same long-term behavior. So now we know that this one diverges. So the last thing we have to do is argue that these two have the same behavior by the limit comparison test. I'll keep calling this b sub n. I'll call this c sub n. So now let's look at the limit as n goes to infinity of b sub n divided by c sub n. Limit as n goes to infinity of n minus 1 divided by n squared plus 5, all of that divided by sine of the same thing, n minus 1 divided by n squared plus 5. Now here's the thing that we should remember. I alluded to this up here. Now I'm going to make that precise, because now we're doing everything for real right now. The limit as n goes to infinity, my mind just wants to automatically say that. I've been saying that so often. This is the limit as x goes to 0 of sine x over x is equal to 1. And also, the limit as x goes to 0 of x divided by sine x is also equal to 1. So, what we can do here is that we can conclude that this limit here is 1, because as n is going to infinity, n minus 1 over n squared plus 5 is going to 0. And we know that we have these limits to be true. What the point here is that this is 1, a finite positive number. And so, by the limit comparison test, this diverges by the limit comparison test using this series, which is diverging by the limit comparison test when we're using this series. So 2 applications of the limit comparison test in this problem.